So yeah, okay, maybe we can start. So yeah, as we promised, today we'll discuss all the questions we have given you. So yeah, also first we'll ask you if you have a solution. Then if you have it, then you can say it with as much less noise as possible, and then we'll discuss our solution, whatever we have, and then yeah, it goes on like that. So yes, so what we'll do, puzzle solutions and more puzzles. So yeah, this is the first question we gave you to do. So again, okay, I'll repeat the question again. So I have a line, okay, an interval 0 to 1 and a unit square, right, 0, 0, 1, 1, right? So can you have 1, 1 mapping between these two things? Like if I give you a point in a square, it should give a point in a line, and if a point in a line, it should give a point in a square. It should be a bijective function. So does anyone have? What did you do? What is your ideas? Hello?
Yeah, you're audible.
Okay. So no one has any answer. I'm assuming that's the case. Can someone tell me that's the case? You're not able to get anything.
Can we do this that we will make the squares strips of straight lines, and we will map it in the means we will make the same number of divisions as those on the line and on the square, and we will map those divisions onto the strips of the square that we get.
But how will you put those many? You'll have basically infinite number of strips, right? How will you? Each strip you have to map to the line, and all those strips you have to pack in this one line. How are you doing that?
I was trying to do something, and there were overlap of points. I mean, 2 points are mapping to same place on the straight line. That is not correct,
That is
right?
not. Yeah, that is not acceptable. Yeah, that's what.
Okay.
Two people should not sit in the same seat. Everyone should have a different seat. Every guy in the square, if this line is a number of seats and these are all people, everyone should sit in a seat and no seats should be empty, and only one guy can sit in a seat basically. That's what bijection is. So yeah, we'll so this is the idea. I mean, can you see what is the solution? Is it obvious from the figure? Can someone tell me how the mapping is going on? So yeah, so points in this unit square, I can represent in base 2 as something like 0.0011111110 something like it's a some it has a representation, right, in base 2. It only has zeros and ones. So what I'll do, I'll pick all the odd digits, put it here, even digits, put it here. That will be my x and y coordinates. So yeah, if you give a point in line, I'll give you this point in square. If you give me this point in square, I will again alternate them and get this. So it's 1 to 1, right? So for every point, I'll have a point in the square. Is it clear? Why it works? It's very simple. You can even generalize it for cube, like pick all the 3n plus 1, 3n plus 2, 3n and get 3 points. Yeah, so basically that says any finite dimensional hypercube, all the points I can map to 0, 1 real line, a 0, 1 interval. So that is a bijection. And is it continuous? Like if this is a slider, if I'm sliding it, will the point move continuously or will it jump? What do you think? Yeah, so maybe think about it, figure
I
out if
think
this
it
mapping
will
is
move in
continuous.
a zigzag manner.
It might jump around. That's what you think.
Yeah, something like that.
Like if I'm moving like this, it might erratically jump here and there.
Yeah.
Right. So maybe another interesting question is, can there be a continuous mapping? So yeah, that is so it's called space filling curves, and it is possible actually. So it is possible there is such a mapping so that if you move it like this, it'll smoothly cover all the square. Such a mapping is also possible. I'm not sure about whether this is already such a smooth mapping. I have to check, but maybe it's not. So anyway, so yeah, coming back to logic puzzles, which we like. So again, I'll restate. So you're dead and you find yourself in front of two portals. One of them leads to paradise, one to eternal doom. You don't know which is which, and there are two guards in front of each portal. One of them always tells the truth, and other always lies. And obviously, you don't know who is who. So the first level question I may ask, I post is, you can only ask one yes or no question to just one guard, and they'll answer yes or no. The second variant will come to it. So what question should you ask them in order to find out which portal leads to paradise? So I remember someone gave an answer, so can they repeat it? Or if it's not the same person, someone else.
I think it was to ask the other person what would he say if I ask him, is this the door to means whether this is the door to paradise. The same thing to do with the other.
Can you tell the statement properly?
It was, I think, to ask the guards that what would the other person say if I ask him, is this the door to paradise?
No. This is a yes or no question, right? So you have to frame the question in that fashion.
Yeah. So
Yes or no
okay.
means yeah.
Yeah. It's close. So maybe you will ask, would the other person say yes if I would have asked him whether this is the portal to paradise? Something like that. Yeah. Like
Okay.
what, instead of what would he say, you just put it, would the other person say yes if I would have asked them if this was the portal to paradise? Something like that. So that is an yes or no question, and yeah, it works. But yeah, there are many others. This is my solution. So I don't bother about other guys. I'll just straight away ask question about who is in front of me. So I'll go to the right guy and say, if I would have asked you whether the portal behind you leads to paradise, would you have said yes? Basically, it's a question in a question. So the inside question says, uh, okay. So okay, the oral question is, if I would have asked you whether the portal behind you leads to paradise, would you have said yes? So it turns out, oh, if he's a truth guy, suppose if he's the truth guy and this is the paradise, this is a paradise and he's a truth guy, he would have said yes because this is a paradise, and yeah, so he'll say oral answer is yes. If he's a false guy, the original answer would be, if you would have asked him if this was the paradise, he should say no because he lied. Okay. So the ideal answer to would you have said yes is no. But since he lies again, the no will get converted to yes. So whether he is a truth guy or false guy, the answer to this question is yes. So if I would have asked you whether the portal behind you leads to paradise, would you have said yes? So if the paradise is there, both of them will say yes. If the paradise is not there, both of them will say no. So that way you will just know whether this is the paradise or not. We say yes, then this is a paradise. If it says no, this is not the paradise. So that is fine. But my next variant modification was they speak some other language. They say da or ja. How do you solve it then? So if you ask the same question, if he says ja, it doesn't make any sense. How do you solve then? Did anyone try this?
Yes, I have tried it.
Yeah,
And,
so what is your solution?
My question means there are 8 cases, and all 8 cases it is true. So I will stand in front of guard 1, means I have named the guard. So guard 1
Okay.
and guard 2.
So say right and left, okay?
Okay. So
Fine.
I'm asking that I'm asking to the left one, okay? So
Okay.
will the right guard say da if I ask him that behind you there is means portal to paradise? So so there are 8 cases, and if and ja means yes, there's the means left portal is paradise, and if da, then right one is paradise portal.
Yeah. I think that works out. Yeah.
Mhm.
So yeah, I'll give it might be okay. What you said I understood, but it might be complicated for others. So yeah, it has its business, right? What would the other guy say? I don't like it. I don't like the other guy business. I'm just straight away asking. So in my solution, see, it doesn't bother about the other guy. You just go to some guy and ask this. It only concerns about this guy. Like why this is better. Suppose. See, these are not gods, so they don't know that the other guy is true or false. They just individually lie or false. Only you know that one of them is lying and one of them is false. In your solution, we are assuming that they know everything. And so this guy obviously knows what is the answer of the other guy, because he knows that the other guy is false if he is true, and he knows that the other guy is true if he is false. So if I remove that information, every guy just knows everything about himself, no, only that much, and the information about portals. So in that case, this solution will still hold, but that won't work. But anyway, so let's see the solution. So previously, if it is yes, then yes. So what happens? So there is a duality between yes and no. What if you change the question to no? You know what will happen? If there is a portal here, then the answer will be no. If there is no portal, then the answer will be yes. Like if the paradise is here, then whatever you put here, you will get here. If the paradise is here, if you say no here, then you will get yes. So basically, you can just replace the yes no business and then say, ask this question. If I would have asked you whether the portal behind you leads to paradise, would you have said ja? If he says ja, then the paradise is here. If he says da, then the paradise is here. Simple, like it's whether it is equal or not. That information gives you whether it's behind this guy or not. Like equality, not equality. That's it. You have to map those two to this thing. Yeah, you need not. Yeah, you can do it with 8 cases, but yeah, that's not required. You just have to realize the duality that's happening here. Basically, whatever truth value is there is transferring here in case the paradise is here. So just replace it with same or different will tell you the answer. So now, Arnav, yeah, this question Arnav will explain and then.
A question should I explain again?
Yeah, maybe just fastly repeat.
Yeah, fine. Yeah. So basically, the question was there were 2 guys who are sort of prisoners, and there is one jailer guy. Okay. So suppose the jailer guy. Okay, so there are two. Okay, so as I said, there are two guys. Okay, so there's one guy currently say in a room, and say guy A or prisoner A is in the room and the prisoner B is outside the room, and the jailer shows him that okay, the guy B must come and point out to this coin here, suppose. So and the prisoner A is allowed to flip one coin. Okay. So before all this thing happens, A and B can make any strategy, but there must not be any kind of communication between them after that. So the question is, which coin should the prisoner A flip, and what should be the strategy so that when the prisoner B comes, he can identify that this was the coin which the jailer was indicating at. So this sort of the problem statement which we posed 2 weeks ago. So before going to 8 cross 8, why don't you try to give an answer for this small box here, both, which is 1 cross 2. So suppose I want you to point towards the second coin, then which coin should you flip? So that's the question. So can someone from the audience try to answer this first basic question at least?
They can decide that if both are tails, then it means that it is the second board, if second right square, and if both are heads, then it is the first square.
Okay, so
yeah,
no means yeah, in a way, but is there
Okay.
any particular strategy which you're using?
No. What if the coin is in the second board, second square,
Yeah.
and it was initially in tails position? So okay, what was your thing? What did you say? If heads heads, then right one, tails then left one. Okay, right. So what if it is in right one and it is in tails? Then you cannot make it go to headsets, right? In one flip. So that won't work.
We can do this that we will change only the first place. Means if it is head, then it is at the first place, and if it is not head, then it is at means if it is not head, then it is in the second box actually.
Yeah, okay. Something like that works. Yeah.
Yeah, something of that type works, but okay, so can, like what you said, can you generalize it like in a way? Like, okay, the hint is if you consider say heads to be 0 and say tails to be heads to be 0 and tails to be 1, like you represent it in terms of bits, then can you use some bitwise operation to like mathematically get the place which you are indicating? Like the logic which you told is fine, but mathematically can you do, like you have AND operation, you have OR operation, you have XOR operation. So can you do any such operation between them and get this kind of like situation?
We may find out some value, and like here I think we can do that if it is 0 1, then means we can assign value position to the first bit as 0 and second bit as 1, so tails is 0 and heads is 1. So here I think if we do this, that if the sum comes out to be 0, then it is in the 0th box, and if sum comes out to be 1, then it is in the second box. Means considering that heads is 1, tails is 0, and the first box has 0 value, the second has 1.
It doesn't work.
Oh,
Suppose,
sorry. I made the mistake in the hint. Sorry. Like what?
Yeah.
Okay. You assign bits to the positions actually, and then do some XOR this position of the boxes, and then do some kind of XOR operation to get the location of this key actually, like of this coin or whatever. Okay, so I'll explain with respect to these two things. It will be clear for 8 cross 8 also. Okay. So first see in which positions you have tails actually. Okay. So like in the original configuration. Yeah. Okay. So in the original configuration, suppose you had tails in both configuration. So this is position 0 and this position 1. So can someone tell XOR between 0 and 1? XOR between 0 and 1?
1.
1.
Yeah, it's 1. Okay. And then you do XOR with this particular thing, it will still remain 1. Okay. So what you do, you flip you flip the tails position. Okay. So this one position. So it becomes tails head. Okay. Tails head. Okay. So when the second guy comes, he sees the configuration is TH. So what he does again XOR of those positions which have tail in it. Okay, so TH. So only the first position is tail. So he does XOR 0. So 0 means it will be here in the first position. I better it will be if I take a 8 cross 8 example itself. Okay. Um, okay, so assume that this black coins are like these black positions are tails and rest all are heads. Okay, and the jailer wants you to point out to this particular position. Okay, and the solution is you must flip this coin. I'll explain why, but you must flip this position. This position is position number 27. Okay, so these are the positions where the coins which face tails upward is situated. Okay, so 2, 13, 70, 50. Okay, yeah, this is 2, 13, 17, and 50. So you you can convert it into binary. Okay, and you can do XOR. Okay, like this is bitwise XOR you can do. So you can do it and you'll get something of this type. Okay, so we'll call it as T. Okay, and this is the position which jailer wants us to point out. Okay, so it's 27. Okay, so what that prisoner A will do, he will do T XOR J. Okay, he'll do T XOR J and he'll get 55 as the position. So 55 is nothing but this position and he'll flip it. Okay, so then when the prisoner B comes, he sees that this, and this. These 5 coins are tails. Okay. So now he does XOR of all the tails. And he gets 27. And that's the coin which jailer was pointing. Now the question, I hope at least the strategy is clear. Like, is the strategy clear? Like this strategy, what exactly it's going on?
Yeah, it is understood.
Yeah. So now let me explain why this strategy will work actually. Okay. So, okay. So XOR has the property that if you do anything XOR with itself, like if you do, say, if you have a string X and you do XOR with itself, then the final outcome will be 0 actually. Okay. So that's the XOR. Like if you take bitwise also, 1 XOR 1 is 0, 0 XOR 0 is 0. Okay. Similarly, if you do for strings and you do bitwise XOR, by bitwise XOR means this bits like leftmost bits you do XOR and then you write it at the leftmost position. Sorry, it's right actually. So rightmost bits you do XOR and keep it in rightmost position. So this is how you do XOR. So same thing works for strings of this type. Okay, if you do XOR with itself, it will turn out to be 0. Okay, so uh, here, what is X actually? It's T XOR J. Okay, and what is this particular quantity here? It's nothing but T. So what you are doing, basically you're doing T, XOR J. So that T XOR T gets cancelled out completely. Okay. And only the J terms remain. So which is this. So this is basically the rough idea how you solve this problem. Here. This problem here, this is the rough idea how you approach it. So can someone from the audience just like re-explain what I told, like in case I just want to check whether you got it or not. The idea, at least.
Yeah, I can try. So
Yeah.
here you said that there is a position. We are giving all the squares some number position from 0 to 63, and
Yeah.
then we are taking up the tails on the chessboard, ignoring the heads, and we are doing XOR with each of them individually. And when
Yeah.
we are doing XOR, we are getting some value, and
Yeah.
then again we are doing XOR of that value with the position at which the coin is there. And when we are doing XOR with that value, we are getting the position at which we should flip the coin. So when we means we should flip the coin at that position if it is not tail. If it is already tail, then we know means we
No,
don't
it
need to
won't be
flip that
tail
coin.
actually, I guess. Or it can be tail, but you must flip it. Like just flip it, I guess. Yeah.
Okay, so we will flip that position, then whatever. So when the next person comes in, so he will again calculate the, he will again see all the tails, and he will XOR them up with the value which he has, means whichever coin has been flipped. So I think we have to make it tail, because unless he has made it tail, he will not do the XOR with the that means he do XOR with X, and X is the position which he has to flip. So he will do XOR only if that is tail.
No,
No, X.
it
No, no,
doesn't
no, no.
matter. Just do this, it will
No.
work.
Yeah, just do this actually. I just took an example where it turned out to be heads. Suppose every coin was tail. Then every coin on the board was tail up. So that so there won't
Okay.
like yeah.
Then
So
exactly what will happen is you will go and flip the coin which he pointed out. You will
yeah,
flip it.
basically.
And it turns out if you take XOR of all values except that one, you'll get this value. Right? You understand? Like suppose all of them are tails and jailer pointed at 55. If you go and flip 55, there are all tails except 55. If you now XOR all of them, you will actually get 55.
Okay.
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 Yeah. Okay. I'll
Yes.
give. I'll tell a very simple explanation now. Okay. I'll modify the puzzle. So instead of pointing out the exact, so the jailer won't show a square. He'll tell odd or even. To B, he'll tell odd or even. And A should repeat that. That's it. How will you solve this? There is a chessboard, coins in some position. You should exactly flip one coin. Jailer will tell 0 or 1, odd or even. Then he'll flip some coin and A will come and see, and he should say 0 or 1. So this simply, again, you look at all the coins with tails, all the places with tails, and add them up. If the number is odd, you flip one of the coins with which is odd number. Then the sum will become even. Right? Okay. What I'm saying is, suppose the jailer said even. You sum all the numbers which has tails in it. If you get an odd number, you will flip one of the coins in this which is odd. Then the sum will turn out to be even. If the jailer said odd, then you just turn one of the coin which is even. Then it will remain odd. So that is exactly what is happening here. So odd or even. So basically, you're deciding the first digit of it, right? The first digit, whether it is 0 or 1, you're trying to say it by flipping an odd coin or even coin. You're imparting the data of the first digit. Again, the second digit also something like that. overall, it comes down to one particular number. Yeah, maybe you study it, but it's very, XOR is a very simple thing. In cryptography also, we can use like, say, there is some text and there is some key. Simply XOR the key with the whole text. Then give that key to some other guy and give the encrypted text. If he re-XOR it, he'll get the original text. So yeah, I'll share screen again.
Yeah.
So that is with this puzzle. Maybe you spend some time. XOR is it's a very useful thing. Okay, this puzzle. So how many of you have done 12 identical balls? One of them is faulty. 3 weightings you have to find. So many people
tried I tried it doing like I took 6 balls, any 6 random, means I had to do some manipulations to get the answer. Means like if I took 6 balls at first, then I weighed 3 of them. Then for some cases, like if I get them, and means I did like the 6 balls first, then like if they are equal, then I will take from the rest of the 6 balls 3 balls, and from these 6 balls I will take any 3 balls and weigh them. So if they are unequal, then I know that the 3 balls that I took now, which I
What
took
if it's equal?
recently, they are
I
actually.
understand. But what if
So
they're equal?
yeah, that is not getting solved. If they're equal, then I'm not getting
So
a
that
solution.
means that you started out wrong. So the way you started out, it cannot solve it in 3 ways. Like what you're doing, 3 and then if equal, then another 3. If they're equal, it doesn't work. Something else. People are trying to say 4 and something like that. So someone?
That would work if that the ball is either heavier or lighter. But if we don't know it is heavier or lighter, then it won't work.
Actually, if you know it's heavier or lighter, I can do it with 27 balls. Give me 27 balls in 3 weighings, I can find out the ball. Right. In each weighing, I'll get by 3. 27 will become 9, 9 will become 3, 3 will become 1. 3 power n will work. If you know if it's heavy or lighter. That's why it's 12, it's not 27. You don't know and you have to find it. So people are close, like weigh 4 if they're equal, it's done. If they're not equal, something.
Like in that problem, when we weigh 2, it is not equal. One will go up, one will go down. Now still we have to weigh both of them, right? Because we won't know in which of it is it.
Yeah, then maybe 2 is bad. Weighing 2 at 2 is very inefficient. It won't.
We can take 3 and weigh 2 of them. If none of okay, I got an idea.
No, actually, dividing them into 4 is the first correct step. Okay.
Okay.
So yeah, so first of all, yeah, numbering them is good. Label them 1 to 12, and then let's have some color codes. It's white if we don't know anything. We did not weigh it, so we don't know anything about it. If it's blue, then it's accused of being heavy. It's not confirmed, but it is either normal or heavy, something like that. And if it's yellow, then it's either normal or light. It's only either of these two. If it's gray, then it's confirmed that it's normal. Okay. So first of all, this can anyone answer? You have 3 balls, and I know the fault. Can you find the ball in one weighing?
Yes.
So how do you do that? So suppose
We
9,
take
10,
2
11.
balls and weigh them.
Yes.
And
So I know that one of them is light, then I'll weigh 9 and 10. If 9 is greater than 10, then 10 is lighter. If 9 is less than 10, 9 is lighter. If 9 is equal to 10, 11 is lighter. So basically in one weighing, I'll know which of them is a faulty one. If I know it's fault. If I don't know, then it's not possible. So right. So how do I do the first weighing? 1, 2, 3, 4, 5, 6, 7, 8. I divide into groups of 4. 3 groups of 4. So I weigh these 4 and these 4. So it could be this way or equal. Let us deal with a simple case, equal. So this 4 and this 4 balanced, right? So then I know that 9, 10, 11, 12 are either all, they have the heavy ball or they have the light ball. And in these two cases, these are normal. So in this case, I can say that all these 8 are normal. Then what will I do? In the 9, 10, 11, I'll pick 3 and I'll pick 3 from here. I'll weigh them. So if it goes this way, it means the heavier ball is in this. If it goes this way, then there is a lighter ball in this. If it is equal, then the odd ball has to be in 12 and it is either heavy or light. And yeah, I think you can just find it out by weighing with a normal ball. If it goes down, then it's heavy. If it goes up, then it's light. So again, these cases, like previously in 3 balls, you know whether it's heavy or light, then you can do it in one way, right? Out of 9, 10, 11, this case, 9 versus 12, and we know what 12 is. And in either this or this case, as we previously saw, we'll just know by weighing 9 and 10. So basically, third case is over. Like if these two are equal, in next two weighings, I can find out which is the oddball and whether it's light or heavy. So now the hard case is when, this went down and this went up. Then we know that these are normal. In two weighings, we have to identify the faulty one. So what will we do? I'll pick 1, 2, 5 and 3, 4, 9. Basically, 2 heavy, 1 light and 2 heavy, 1 normal. And put the 3 light and 3 normal away. So if it goes this way, then either 3, 4 is heavy or 5 is light. If it goes this way, then only possibility is either 1 and 2 are heavy. If it's equal, then there is a lighter in 6, 7, 8. All these are gray. 1, 2, 5, 3, 4, 9, 11, 10, 12. So this case we already know. So how to deal with these two? So 1A is harder than 1B. So 1A, if we solve, it's over. So 1A is simple. We know that either there is heavy in 3, 4 or lighter in 5. You just weigh 3 or 4, 3 and 4. If it goes this way, then 4 is heavy. If it's this way, then 3 is heavy. If they are equal, then 5 is light. Right. So yeah, basically this one in one more weighing, I can tell which is what. And this is also same. Weigh 1 and 2 and you'll know which is heavier. So that's it. So this case 1 is done. Case 2 is just these are blue and these are yellow. That's the same thing, right? So that's it. In 3 weighings, you can find out which ball is what. Is it clear what happened? Just cleverly, by the outcome, you have to cleverly regroup them and reweigh and then extract as much information as possible. Right, so that's it. So given 12 balls and I can identify which is the odd one and tell you whether it's light or heavy. Actually, an interesting question is, so our strategy is very serial, meaning if this happens, do this, like it's a branching, right? What we do, you do this and then if this happens, then this, if this happens, then this. Our next move depends on what happened previously. It's chronological. But can you just, it turns out that there is a weighing, like you say, I'll do this, I'll do this, I'll do this. And then depending on the output, it's like 1, 4, 8, 12 and 5, 7, 10, 11, 2, 6, 9, 11, 4, 7, 10, 12. These three weighings you do, and depending on the outcome, equal, equal, left, equal, equal, right, equal, left, equal. We just have third is lighter, third is heavier, or second is heavier, or ninth is heavier, or sixth is heavier. It's basically 12 into 2 possibilities, 24. So basically 24 possibilities mapped from, see, it turns out of 27 possibilities, basically 3 into 3 into 3, all 27 are not possible, because all 3 equal is not possible here. It means that all of them are equal or something like that. So out of 27, some are not possible, and the rest 24 are mapped. So again, generalization is a motto of mathematics. So 12 and 3 is very specific, right? So the general puzzle is, you have 3 power n minus 3 by 2 balls. You can see that if n is 3, 27 minus 3, 24 by 2 is 12. 12 balls, 3 balances. The generalization is this: 3 power n minus 3 by 2 balls with n balances. You have to identify the faulty ball and say it's whether it's heavier or lighter. And again, the 13 balls thing is more or less something like this. I increase one ball and you need not say whether it's heavy or light. So it is more or less like this. Maybe you can try. And yeah, that is this 3 power n minus 1 by 2 balls, and do it in n balances. So 27 minus 1 by 2 is 26 by 2, 13. 13 balls, 3 balances. Identify the odd ball. So these two are generalizations. It will be nice if you can give a strategy for this, like maybe inductive, like assume that you know the strategy for 3 power n minus 1 minus 3 by 2 balls with n minus 1 balances, and find it out for the next thing. Yeah. And yeah, Arnab will continue with the solutions of question 5 and 6, and yeah.
Yeah. Yeah, so last time I gave 2 questions from graph theory. So in case you forgot the definition, just stop me in between, I'll tell it again. So suppose we had a graph with n vertices, and I said that every vertex has a degree at least n minus 1 by 2. Then I said that the graph is connected. By graph is connected, I meant that there is a path between any 2 vertices. Okay, so you take any vertex, any 2 vertex, you can like start from one vertex, start walking on the graph and reach on the other vertex. So it's possible. Okay. So there is a simple proof for it. Okay. So suppose, okay, so obviously we should be looking at a case where X and Y don't have an edge between them. If they have an edge, then it's already they are connected, like they are adjacent to each other. So you take 2 vertices which don't have an edge between them. Okay. So now, can somebody tell what how many vertices will be there in the remaining portion of the graph?
N minus 2.
Yeah. And and the degree of every vertex is n minus 1 by 2. So see, there are edges which are coming out of these vertices. So can someone tell the some number of edges here, like minimum number of edges which will be present here, like these edges which have been highlighted?
Yes, so it will be twice of n minus 1 by 2. Means if they're not
Yeah.
making a connection
Yeah, yeah.
from other points.
Yeah. So it will be, so basically you have n minus 1 edges, but you have n minus 2 vertices. So it means that there will be two edges which are incident on same vertex. It's pigeonhole principle. You have n minus 2 holes and n minus 1 pigeons. So two pigeons must go to the same hole. So it's happening. So so basically two edges are going towards the same vertex. So basically they are connected in this fashion. So you can start here, go to this vertex and then reach here. So this is the basic idea of the proof. So I hope the proof is clear. Is the proof
Yes.
clear?
Yes.
Yeah, okay. Yeah. So this was the rough idea of the proof. Next, what I asked to show, like last time there was some like internet connection problem, so I couldn't explain the problem carefully. So I'll explain it again. So if we have a graph on 2n vertices and it has more than n square number of edges, then I told that the graph contains a triangle. So by triangle, I meant that there are three vertices such that each of them is adjacent to each other. Means each of them has an edge between them. So yeah, like is the definition of triangle clear, or should I explain it again?
Clear.
Clear, right? Okay. Just 1 second. Okay. So I gave one proof last time, but I wanted an alternative simple proof, like using mathematical induction and pigeonhole principle. So what we can do, we can do induction on this n. Okay. So for n is equal to 1, we have two vertices. Okay. So for two vertices, this statement is true because two vertices cannot have more than n square edges. Okay, in first place, two vertices can have a graph with two vertices will have only one edge. Okay, so if this is a statement of this type, like if then if and then, like if this is true, then this is true. So if if part is not true, then the statement is said to be true actually. Like that's the logical thing. Like you must have done in your JE actually. P implies Q. If P is false, then P implies Q is true. That's the truth value actually. That's how we do truth. If then truth thing. So that's why the base case is quite trivial. So for n is equal to 2, this statement is correct. So now we'll do inductive hypothesis. So we'll assume that for a graph on 2n vertices with more than n square edges, we'll assume that the graph will contain a triangle. Okay. So this is the inductive hypothesis. And now what we should be trying to prove is if the graph has 2n plus 2 vertices and has more than n plus 1 square edges, then the graph has a triangle. So this is what we want to prove. Okay. So now let's consider a graph with 2n plus 1 vertices with n plus 1 square plus 1 edges. Okay. Okay. So let us consider a graph where x and y are adjacent. Okay. Sorry, let us consider two vertices which are adjacent, means they have an edge between them. Okay. And let h be a graph which we get by deleting x and y. Like basically, like for example, so if you delete these vertices, then even these edges will also go. And what you're left with is another graph actually. And that graph we call it as h. Okay. So imagine in that fashion. Okay. So that graph has 2n vertices because we are the entire graph G. The entire graph G will have 2n plus 2 vertices. So if you remove two vertices from it, it will have 2n number of vertices. And if we have n square plus 1 edges, then by induction hypothesis, that smaller graph will contain a triangle. And since that smaller graph is part of the original graph, it means the original graph will also contain a triangle. So this is one part of the proof. So suppose that this remaining portion doesn't contain n square plus 1 vertices, as we are claiming here. So here the claim was it contains n square plus 1 edges, sorry. So if it doesn't contain, so this n square, sorry, this superscript. So suppose it contains n square edges. Okay. So can someone tell me how can we guarantee that we'll have a triangle here? Like, can someone from the audience try to give a answer why we'll have a triangle now here like this? Can someone try? Hello, am I audible?
Yes.
Yeah. Like, can someone tell? It's quite simple actually. Okay, then I'll only tell it. Okay. So here we have like n square number of edges at max. Okay. So it means that here, these edges which I have highlighted, it will have at least 2n plus 1 edges. Okay. But there are only 2n number of vertices here. So it means that by pigeonhole principle, two edges must go to the same vertex. Okay. And since x and y had an edge between them, this forms a triangle. So this was the pigeonhole. This is the part where we use pigeonhole principle. So that's why this thing will hold true. Like we showed this part basically. We showed that if graph has 2n plus 2 vertices with more than n plus 1 whole square edges, then the graph contains a triangle. So that's what we showed actually. So assuming the inductive hypothesis we used here, and the pigeonhole principle we used it here. Yeah, so this was the overall idea. So like in case, like it's a very simple proof. You can have a look at it again and share the slides. Yeah, Madhu, you can take over.
Yeah, okay, so complicated stuff is over. We'll just wait. Closed it in a second. So we'll look at two more puzzles. Okay. I'll share it.
I had a question. Do we have the any graph theory course in our engineering?
Yeah, in fourth, actually, okay, so there are two ways you can take the course. One is being offered by Maths department and other by CS department. So in case you are from CS or Maths, that will be part of your like we call something called electives. If you're not from CS, then you can apply it as additional and you can take it later.
Yeah, so there are many ways you can learn. Yeah, you can take from via electives you can learn or additional or yeah, there are many ways. Yeah, courses are there. So two more puzzles before we end this session. So the simple was okay. A king wants to marry his daughter to the smartest of three extremely intelligent young princes. So there are three people, and so the king's wise men devised an intelligent test. What it is? So the princes are gathered in a room and seated, facing one another. So they are sitting in a triangle, say, and everyone can say each other, and they're shown 2 black hats and 3 white hats. So out of 3 black hats and 2 white hats, so they're shown these 5 hats and they're blindfolded, and out of these 5, one is picked. 3 are picked, and each of them goes to one of them, each one of them. So basically, you select 3 out of these 5 and put it on each of them. So one hat is placed on each of their heads, while remaining hats are hidden. Okay, fine. So the king tells them that the first prince who can deduce the color of the hat on their head will marry their daughter. Okay, and the wrong guess will mean you'll die. And then the blindfolds are removed. So what happens? You are one of the princes and you see 2 white hats in front of you. So you can be a black hat or you can be a white hat. You don't know. After some time, you realize that the other princes are unable to deduce the color of their hat and are unwilling to guess. So what color is your hat? So assume that everyone is highly intelligent. So the question you understood, right? There are 3 people, 5 hats. I'll pick some 3 of them and put it on their heads, and they don't know which 3. And you opened your eyes and then you see 2 white hats in front of you. After some time, you realize no one is answering. So you somehow are able to deduce the color of your hat. What is it and why? So any thoughts? I assume you understood the question. You can try it. It's not very hard.
I think it should be white only.
Okay, someone thinks it's white.
Is the last one allowed to speak only? Or anyone can speak?
No, at any point, anyone can tell the color of their hat. And if it's right, they'll get to marry.
I think the middle one will speak out and say it is he is wearing a white one.
Not middle. I mean, you open your eyes and you're seeing 2 white hats. That's it. So you are able to answer. How?
Okay, so if just a minute.
Because right, if we because we will see that like name them 1, 2, 3. If we are 1, we will see that the guy with the guy at number 2 is not speaking up, whereas he is seeing a white hat and the hat at my head, which could be either black or white.
Okay.
So if it would have been black, if although the answer is that over my head it would be white, but if the hat at my head would be black and wait a second.
Yeah, it's a little bit nested, but not so much nested. Yeah, the way you're thinking, it should be evident after a while.
One thing is that no one is saying 2 black hats.
Yes. Okay, that is the point. If you see 2 black hats, then you are obviously white, because there are only 2 black hats. This is one point.
This is one point that every prince will, have noticed that. That's why other princes are not able to tell, because this is surely not the case.
Yes. Okay.
So now the possibility is there are 2 white hat and 1 black hat, or there are 3 white hats, because one of the prince is saying 2 white hats. So
yeah, I mean, you have to deduce from your point of view, right? You are seeing 2 white hats and then just deduce. That's it.
Okay. Yeah. So
like only from your knowledge, you have to think what other people are thinking, that other people are thinking or something. Yeah.
Am
Is
I
it
the
based something on probability? Means probability that his hat will be this color or something like that.
No. It's not probabilistic. It's you deterministically guess that your hat is some color, and you're the most intelligent guy. Like those two are not able to deduce anything, and you're using that knowledge. You're able to say something.
the other two people are blind?
No, they're not blind. They're also seeing, but they're silent. They're not sure. Like initially, you see two white. You're not sure, right? If it's black or white. Maybe some similar reason they are not able to deduce. So they remain silent, and you use this information to deduce that.
If yeah, right, we can see that there are two white hats,
Yes.
right? So they
Yes.
can be either one black hat, or they can only be one black hat, or right. If there have been two black hats, then
No,
have
right.
definitely said
It
that I
it
know
can't
by
be.
the color of my hat.
Now, can you say that? Can you deduce properly? Like you are seeing two white hats. That's it. So what are you thinking?
Wait a second, I'll answer. Just a second more.
So yeah, okay. Think about it. Second one is also similar, but with the hats
answer
and
is
stuff.
I think all the three are wearing white hats. Can I say the solution?
So you're saying you deduce that you are wearing a white hat. That's what you're saying.
Yes, I am wearing a white hat.
How? How do you think?
Okay, so uh, okay, so the thing is, I assume, I mean, if I were to wear a black hat, okay, so I would think that the other person will see one black hat and one white hat. Okay.
Yes.
So, and I mean, I am numbering. Okay. So for the sake of simplicity, suppose I am number 3. Okay. And the other two are number 2 and 1. Okay.
Okay.
So, I am seeing from the perspective of number 3. So, from the perspective of number 3, I assume that if I were to wear a black hat, then the person number 2 would
Yes.
see one black hat and one white hat.
Yes.
And he would say that person 1 and 3 are not able to deduce their color of hat because I am wearing a white hat.
Yes.
Because if he were to wear a black hat, then one of them must be able to deduce the color. Because one of them would
actually, yeah, not one of them, not both of them. Number one will be able to see two black hats.
Number one will see two black hat and he will deduce the color. So in this way, if the number 3 is wearing black hat, then number 2 can deduce. I mean, number 2 can speak up.
Yeah, after some time, number 2 can say that he is white. And even that didn't happen because
even that didn't happen. So that's why number 3 is wearing a white hat.
Yes. Yeah, that's it. It's a two-level logic. Somewhat like you think
it's two-level. It's
you
similar
going to
that
one person's head inside a head, something like that.
It's similar to that green-eyed and blue-eyed problem.
Yes. Okay, here is a more maybe a little bit harder. So you have a mad king, 100 people. So what he'll do, he'll make them stand up in a line and put either red or blue hat on each of their heads. So it's not all red or blue. Red, blue, something like red. Some random thing he'll put, okay? And they'll make them stand in a line in ascending order of their height wise. So they'll stand height wise. So the last guy will be able to see all the guys in front of him and what they're wearing. The shortest guy in the first will not see anyone. Okay. So what he will do, he'll go to the tallest guy and ask his hat color. He'll say something. Okay. If it is right, then okay. He'll not kill or something. Yeah. What is there here? If the answer is incorrect, then the wise man will be silently killed. If the answer is correct, then the wise man may live, but remain. Yeah. So they'll keep asking. They'll go to the tall guy and ask, "What is his hat color?" He'll say something. If it is right, then they won't kill him and go to the next tallest guy. If the tallest guy answered wrong, then he'll be silently killed. People won't know that he was killed. Okay, then they'll move to the next tallest guy. So they'll keep doing this, and they'll come to the shortest guy. So this thing will happen. So they know, the 100 people know that this is going to happen the next day. So they have to come up with a strategy so that maximize their survival or something like that. If they randomly guess each of them, then in expectation 50 people will live. But for maximum people to live, what should they do? What strategy should they come up with so that as many people will live? And how much is that number and why? What is their strategy? So this you can think. So don't try to answer. You just try it. This one was not that hard. This might take some time. It's not very, very hard. It's okay. So anything else you want to ask?